Hey guys, in this video I will present a solution to IMO Short List 2015 problem N1. Firstly, let's have a look at the statement. Consider a positive integer capital N and define an infinite sequence A0, A1, A2 and so on by A0 equals capital M plus 1/2 and AK plus 1 equals AK times the floor of AK for all subsequent terms. Now we are asked to determine when this sequence contains at least one integer term. A possible simplification for the problem is to only consider, so we assume that M is an N such that, well, the sequence AI doesn't contain an integer. For such M, our sequence AI is really nicely defined because the floor of AK is always going to be AK minus 1/2. And because it is always nicer to work with integer sequences, we shall define a new sequence, BI equal to 2AI. And then of course all of the BI's are going to be integers, namely B0 equals 2M plus 1 and bk plus 1 over 2 is equal to bk over 2, and those 1/2 cancel out, times bk minus 1 over 2. And now if we take a look at this sequence, our assumption tells us that bk is odd for all indices k. And we want to think of this recursive definition using a function. I'm going to define f of x to be equal to x times x minus 1 over 2. So this tells us that bk plus 1 is equal to f of bk. We are given that all of the terms bk are odd. So let's take a look at when f of x is going to be even, because this restricts the possible values for bk. So let's take a look at what happens for b0 is equal to 2k1 plus 1. In this case, we can compute the value of f of b0, which is nothing but 2k plus 1, 1 plus 1 times 2k1 plus 1 minus 1, all divided by 2. That is equal to k1 times 2k1 plus 1, which is congruent to k1 modulo 2. So the value of f of b0 modulo 2 is not restricted by the parity of b0. We have to consider the parity of k1. Therefore, we get the following two cases. Firstly, that k1 is odd, in which case we get that b0 is equal to 4k2 plus 3, or b0 is equal to 4k2 plus 1. In this case, we get that f of b0, which is b1, is congruent to 2k2, which is 0 modulo 2. But of course, that is a contradiction because b1 is odd. In the other case, we will not be able to finish because we get that f of b0 is going to be congruent to 2k2 plus 1, which is 1 mod 2. So we have to then take a look at the parity of k2 to get the value of f of b0 modulo 2. The first case being that k2 is odd, which gives us b0 equal to 8k3 plus 3. And on the other hand, we have b0 equal to 8k3 plus 7. In that case, f of b0 equals 8k3 plus 7 times 4k3 plus 3. All of this is congruent to 7 times 3, which is 1 modulo 4. But since f of b0 is equal to 1, this tells us that b1 is equal to 4k2 prime plus 1, which leads us to this case, but we have already found out that this leads us to a contradiction. In particular, we will get that f of b1 will be even, so b2 will be even, but this is a contradiction to bk as well. This case is going to lead to f of b0 equal to 4k2 prime plus 3, which is not going to be enough to finish immediately. So let's consider the two cases, b0 equal to 16k4 plus 3 and b0 equal to 16k4 plus 11. In this second case, we have f of b0 equal to 16k4 plus 11 times 8k4 plus 5, which is congruent to 11 times 5 or 7 modulo 8. This leads us into that case, which we have already shown leads to a contradiction, and therefore b0 also can't be 16k4 plus 11. We might hope to be able to continue this scheme and therefore come up with the following claim. If x is congruent to 2 to the power of n plus 3 modulo 2 to the power of n plus 1, then f of x is congruent to 2 to the power of n minus 1 plus 3 modulo 2 to the power of n. This is exactly the behavior which I've notated with these green arrows before in a formalized and general way. The proof for this claim is purely computational. Just plug in x equal to u times 2 to the power of n plus 3, where u has to be odd, and then do some computation of this form exactly, which we have done with concrete numbers in those cases, and you're going to see that this must always hold, and a proof is also in the PDF on our website. Now, from this picture, we can pretty much instantly see that b0 must be everywhere in the first row, because otherwise we would be in some case in the second row, which is formalized by our claim that we are going to be able to go back iteratively through the second row and each column to end up with some index I such that bi is equal to 4k2 prime plus 1, and then bi plus 1 is even, which is a contradiction. So b0 must be congruent to 3 modulo any power of 2 greater than or equal to 4. So b0 is congruent to 3 modulo 2 to the power of n for all m in n. Now, just take m large enough such that 2 to the power of n is larger than b0. For that m, this condition actually tells us that b0 is equal to 3. Now, since b0 equals 2m plus 1, this tells us that m is equal to 1. So we have proven that for all integers m not equal to 1, the sequence ai will contain an integer. The last case is m equal to 1, where we get a0 equals to 3 halves, and then a1 is 3 halves times 1, so also 3 halves, and therefore by induction all of the sequence terms are going to be 3 halves, which is not an integer. Therefore, indeed, our set of solutions is m in n without 1. And therefore, we are done.